Welcome back to my YouTube channel. Today I'm talking about the rnbinom function. This function generates random value from the negative binomial distribution. The required arguments are n, size, and probability. N is not the number of samples we're taking from the negative binomial distribution. Size is the number of successful trials that we're waiting for. So we do trials until we get that number of successful trials. And probability is the probability of success on each trial. Of course, that's actually prob, not probability. Okay, so I'm going to go ahead and start programming. Okay, so I'm going to make a vector x and fill it with values from the negative binomial distribution. As always, I'm going to do 1 million values. I want to set size equal to 1. So this is the number of trials until we get a single success. And the probability equal to 0.5. I'm doing it this way because it's easy to think about. Mu is also an optional parameter if you use a different parameterization of the negative binomial, which is something to look into if you need that. Okay, so I have these values, and I'm going to go ahead and show you the first 8. Hopefully it'll fit in one line. Oh yeah, of course. Okay, so sometimes it takes 2, sometimes the first draw is a success. So it goes from 0, 1 to 2. Of course, that's not actually the highest value. When I did it earlier, the highest value I got was about 8. But let's look. Yeah. With 1 million samples, it can actually vary quite significantly. This time it took 19 trials before that success. So 20 total coin flips. Okay, so let's go ahead and get the mean and standard deviation of this. Okay, so the mean of this is 1. On average, it takes 1 failure before a success. That's great. The standard deviation is 1.41. You might recognize that as the square root of 2, which makes sense because if we do the variance, we get a number very close to 2. Okay. So I want to go ahead and plot this too. We get a lot since 0, as we would expect here, we get the expected value is 1. And then we have extreme values going off into the tail. Let's say that we want the probability of 5 or more. So the probability that it takes 5 failures before we get that first success. So we want counter equals 0 for I in 1 to the length of x. I've been doing this so much. I'm going to be glad when we're done with the data generating functions, but I think getting probabilities by simulation here is an important part of this. Okay, so for I in 1 to the length of x, so the length of x is 1 million, so it's 1 to 1 million. If x of I, that it pulls out the value of x at each element in the vector, is greater than or equal to 5, because I said I wanted 5 or more, then counter equal counter plus 1. Okay. That ran instantly. Computers are amazing. So counter divided by the length of x, and that will give the portion in the tail. Okay. So it looks like a 3% chance that we're going to have 5 or more failures before our first success. Let's go ahead and multiply that by 100, make sure I'm not crazy. But that, even with a master's degree in statistics, I'd not worry about this, but I always gotta worry about it. Okay, yes, so 3% chance that we have 5 or more failures before our first success. Of course, that's an approximation. To really get that value, you have to use the P, Q, or D in binom function and figure out where you are in the tail and where you want to be. But this simulation just gives you an idea of what the approximate value should be, so you're not shooting in the dark. Okay, that's the end of the video. Thanks for watching.